What is the basic principle of uncertainty propagation? And to introduce the concept, I will use a very basic example with one input quantity and one output quantity, and this can be easily visualized in a 2D diagram. So along the one axis there's the input quantity, and along the other axis the output quantity, and both are related by a function. And now if one input quantity is measured, the function can be used to evaluate the output quantity. This measurement could be repeated and another output quantity is calculated, and again. And in principle, a lot of individual measurements could be done. They could be all evaluated with the function and be propagated towards the output quantity. Such processes are done, for example, in the field of Monte Carlo simulation, but that requires a lot of computational efforts. In order to simplify this process, a model could be used, and this goes back to the mathematician Carl Friedrich Gauss, who investigated propagation of uncertainty. The first step is to model the distribution of the values. For this, usually a normal distribution can be used, but also other distributions could be considered. And the nice thing about a normal distribution is now that it is described by two parameters: the mean value, which describes the most probable value, and then the standard deviation, which describes the width of the distribution, and this can be also considered as the uncertainty. Now the mean value can be used and evaluated with the function to get the output estimate, and the next step is to propagate the standard deviation. And to do that, first the gradient of the function is calculated, and this is done to linearize the problem. So the gradient is at the same time the first term of the Taylor series, and this can be then used to scale the standard deviation, and this will then give the standard deviation for the output quantity. And now for the output quantity, normal distribution can be reconstructed, and the standard deviation for the output quantity describes now the uncertainty for this value. To generalize this concept, the absolute value for the gradient of the function should be taken to take into account that the slope might be also negative, but the standard deviation is defined to be always positive. And this could be rewritten by using the square root and by squaring the term. And now this can be then extended also for multiple input quantities.